Welcome to episode 3 of AfterMath, the official podcast of themathcitadel.com. I'm Jason Hathcock, and I'm an editor, designer, and researcher for the website, Jasonographer on Twitter.
I'm Rachel Traylor. I am the lead researcher and founder of the Math Citadel. You can find me on Twitter at Mathpocalypse.
Today we wanted to talk about proofs.
The word's a bit loaded, but we're going to talk about the mathematical kind.
Because proof gets thrown around in English a lot.
Yep, it sure does. Evidence is not proof.
No, it's
I
not.
did a video on that. I should probably redo that video with our nice new format.
Oh yeah, we're gonna redo lots of videos and put up a bunch of fresh content.
Maybe we'll put you on camera this time.
Oh yeah?
Yeah.
Am I camera friendly?
The only reason I think that I'm on camera and you're not is because I suck at being a videographer.
I do like to hold the camera, get the
So
footage.
I don't hold the camera as well as you do, which is why I end up on camera. So yeah, that's why.
So proofs in mathematics rely kind of on this thing called predicate calculus or propositional logic. So a proof, mathematically speaking, is an incontrovertible way of explaining something to be true.
Correct.
In that way, a proof is inarguable. You cannot, break a proof after it's been done, like an actual proof.
Correct. The only way to break a proof, if you will, is to show that one of the steps, the logical steps, is invalid.
Mm-hmm.
There are some subtleties that happen. For instance, it is totally possible to construct a perfectly logical argument, as in the middle stuff is perfectly logical.
Step to step is fine. But
you end up with a false conclusion. Those are the paradoxical proofs and stuff that you see online. 0 equals 1. What really happens there, those aren't proofs. Proofs mean that you start from a statement and you follow from the assumptions of that statement to a conclusion. If X, then Y, meaning you have to start with X.
So that's actually an important notion. The things that are normally proven are called theorems, propositions. We have lots of words for them, but
it's like ranking.
It's true.
Lemmas rank below theorems.
Corollaries do as well. They're sort of like this follows from a theorem.
Well, yeah, corollaries are like another statement of kind of like, ooh, this is illuminating, but it's essentially the same proof. Where do you rank proposition? Is proposition above lemma or below lemma?
I feel like proposition is below a lemma.
I think it generally is used that way, but there's some books I feel like it's used almost as an equal rank.
Mm-hmm. I agree. And that's another thing about proofs and theorems in particular. Because it's all up to the mathematician that's making the proof ultimately, now as though it is all fact and it must all be carried out with, bulletproof logic, mathematicians have a way of inserting their signatures into proofs. They have a way of writing them that is uniquely theirs. And sometimes it's a sort of hodgepodge from what they've learned from various other mathematicians and what they picked up that they liked. But there are hallmarks usually.
It's probably something I don't really have an Archimedean viewpoint on. Can you recognize a proof I've written, assuming you didn't know that it was me who did it?
I might be able to pick up on some of the subtle things that are your handwriting, yeah.
What kind of stuff do you, well, not the hand, you don't mean like physical handwriting?
That was metaphorical handwriting I was referring to.
Okay, so what kind of metaphorical handwriting do you see running through my proofs?
You are very consistently referring to yourself and the reader as a group on a sort of pathway to the answer through the logic.
Well, that's not uncommon. A lot of mathematicians do that.
Yeah, that's not the only thing, but yours is very direct. I think I could probably read it. Also, you like to use the phrase, we have that, and then what you have.
Oh, I picked that up from Dr. Korzanowski.
Uh-huh.
He does that a lot. I picked that up from my advisor.
I personally, I'm very different when it comes to writing proofs. I use a language that actually never says we or I or any of that, and that's deliberate.
Yeah. Jason writes proofs that are very passive. I think the more formal way to do it is actually yours.
Probably so.
I choose to do it a little bit differently because I'm trying to illuminate. I think when we prove something, part of it is when I prove a theorem, yes, I want to show that it's true so that I can use it in other stuff, because if I don't know provably so that it's true, I'm building a house of cards mathematically. So obviously that's the primary objective, is to show a statement is true so that I can build things on top of it. But the other thing that I think is important when you're proving something is illumination. Proofs, unlike what movies or whatever will have you see when mathematicians are just magically working at a board or something, they don't just come out of nowhere.
No.
There may be points of random inspiration, but the entire proof, as elegant as it looks at the end, I promise you they don't start that way. Promise they don't start that way. In fact, it's usually it's like putting a jigsaw puzzle together.
Sometimes a simple paragraph of proof represents months of work.
That's sometimes a line. I try in my proofs to illuminate the reader to my motivations, in that you should be able to see how my thought process got from the statement to its conclusion, and in doing so, you'll understand the limitations of what I've done, what kind of implications it has. To me, a proof should be illuminating. I mean, now there are clever ones out there, right? There's things that we do that's almost a game, right? How few lines can you get and prove something in a really clever, way by reaching very laterally.
Yeah.
I think that's a good, fun game. I don't like that style of proof.
Not for instructive purposes.
Well, if I'm publishing research, and that's what we do, it's not just about me getting it out there and saying I've published it. I want it to be understood. If it's not understood, how can it be used to further something else? And so that's why I try to write very illuminating proofs, starting from as much first principles as I can, and try to make it a little bit more of a group discovery as you read the proof.
Right. Like, a person that picks up your proof should be able to follow it and read it and step by step actually come to the same conclusion you did reasonably. So they should be able to follow your logic. Now, you mentioned the term first principles, meaning that the approach you like to go for with proving, because there are many, is usually direct if you can. That's what's called direct proof.
That's correct. And moreover, for instance, if I'm going to cite a theorem, another theorem, right, in the middle of my proof, I've made, step A, B, C, and at step C, I need to invoke another person's theorem to be able to move forward, then I like to set it up as, well, how did I make that leap to pull that theorem? Well, you can see that we've essentially set up, the hypotheses of this theorem here, and therefore we may invoke it to get the necessary conclusion, as opposed to just, statement, by this theorem, blah.
That's an important thing to note, too. Theorems and propositions, all these things are, and some, they are if-then statements. They're like, if this is, if you have this, then you get this. So what you're saying is, whenever it comes to invoking a theorem like that, you basically set up okay, now you see I have all the if part, and I'm going to get the then. Because, again, I'm reaching, sometimes when I invoke another theorem, it's not obvious. It's a bit of a lateral reach to something else, sometimes even another branch of mathematics that I have to reach to. When I was working on the dependency stuff, you remember how I went through so many ways to try to prove that stuff. In fact, I have an alternative proof. It's just kind of messy, dealing with that class of dependency generators. And I was going to reach to the adjacency matrix of those graphs. And there was a fairly basic theorem in graph theory that gave me what I needed. Yes. And
so I was going to try to reach laterally over there, but setting it up became so cumbersome. I could have done it. In fact, I did it. I just have the written discarded one somewhere.
Yes.
It's not the published proof. But I chose not to do it that way because it was a little bit too much of a setup. It got a little messy. And
some things might have been obscured by taking that approach.
Well, if it's not going to paint a good picture of what's really going on, if I'm just kind of blindly reaching for logical steps that still show it's true, it doesn't make it any less true, but it's not helping me or anyone else understand how to build off it. one of the proofs that I did for the generalized multinomial distribution, I needed that to talk about some of the other ones, like dealing with sequential dependence, and later showing that any class from that, or any dependency structure generated from one of those functions in that class is identically distributed. That proof ultimately was based on the stuff that I'd set up way before. I wouldn't have noticed that if I wasn't very careful, methodical, and direct, because it's partly helping me understand what's going on. The proofs aren't just to show a statement is true and be done with it. I'm trying to understand how these previously uncreated or undiscovered, it kind of depends on your philosophical perspective, how these things work.
The proof is illustrative as well.
Yes, I do prefer that. I do like that.
I believe, wasn't there a theorem in your thesis that relied on trigonometry?
Oh, yeah. It was one of those things. It was one of my crowning achievements of it was this. So picture a puzzle, right? And you know what it looks like. Like, I know what it looks like. I know it's a penguin or something. But you're missing that one last piece in the middle. Like, it's not even at the beginning or end. You need some middle statement to be true in order to tell everyone for sure this is a puzzle of a penguin. So I was stuck. I was stuck on this one statement, and it was a lemma. It was a lemma that I needed to get from one step to another in a bigger proof. And yes, I invoked some basic stuff from trigonometry to make it work. Honestly, looking back, I don't really remember exactly how I built that, other than I was just playing with drawing it out on the board. And it was straight trigonometry and geometry. So what happened was I changed perspective.
Yes.
I remember this now. It was trying to prove basically that a particular slope of a distribution at a certain point was going to be less than 1. I needed that. And I was so focused on the slope, doing everything I can. What do you know when you have slope? How do you get slope? Calculus this, all this stuff.
Absolutely.
And then I drew it out, and it's not just, right? You get slope when you draw it out, but what do you also have when you create a line with the slope? You have an angle with the x-axis,
right?
Which actually in itself contains all that information, right? If you take basically the x-axis and you go 30 degrees above horizontal, you can find the slope and you know the point at which it crosses the x-axis. You've got the slope. It's done.
Yes.
So by changing perspectives and looking at that angle instead, there it was. All I had to show was a statement about this angle, and that was it. And
there's a particularly elegant way to show it. It relies on basic trigonometry. It's fairly easy to follow, and beside it being easy to follow, it's readily seen whenever you make the picture, and the argument is great for that. So you read it, and it follows very nicely. Regarding the idea of a direct proof, there are other methods of proof. One of the most popular ones would be proof by contradiction.
Most popular as in most popular alternative?
I mean, I am fond of proof by contradiction.
Ooh, why? Why are you fond of proof by contradiction?
Because I'm a contrarian.
Well, yes, but I need a better answer than that. Like, seriously, why do you like proof by contradiction better than a direct proof?
I don't know. It just seems natural to me.
No, we should pick this apart. Okay, so to me, proof by contradiction means that what you're going to do is assume that the statement you have in front of you that you're trying to prove, assume it's not true. And then by assuming it's not true, you move in a direct fashion until you arrive at a contradiction, as in an impossible contradiction, like 0 = 1 or something ridiculous like that. And what that means logically is that somewhere along the line, your assumption was wrong. So, right, if your logical steps before you got to that contradiction were correct, then that means the contradiction is due to an improper assumption.
Which you started with.
Which is what you started with, namely that the statement the original statement was not true. So if you get a contradiction, then
your original statement must have been true.
Because you assumed that it wasn't, which was an incorrect assumption leading to an impossible contradiction.
Right.
We should probably diagram that in a video or something.
Probably. It's, yeah.
Proof by it really maybe just like an infographic, because it's one of those things that could use a good infographic now that I think about it. I don't think I've ever seen one.
Yeah, the basic idea is that you say, I want to prove statement A is true. Okay, well, suppose it isn't. And then follow the logic from that all the way to something crazy. The idea is that you get to something, a contradiction. And they say, oh, okay, well, the assumption that it was false must have been a problem. Therefore, it must be true.
Right.
That's what you wanted.
Yeah, I still think a visual diagram would be good. Anyway, to me, though, in the way a proof by contradiction works, you have to start by proving it directly, right? You're doing a direct proof just on the negation of the statement until you arrive at a contradiction. So it's essentially a direct proof, but from a different perspective.
I don't know. Maybe the proofs by contradiction are easier. I'm not sure.
That's what I'm wondering. Why do you find them easier? Because to me, to prove by contradiction, you have to identify the contradiction that you want to come out, right? There's some initial exploration. Assume the statement is not true. So what does that mean? Well, if it's not true, then you get blah, 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 right?
Yeah, now that involves negating the original statement, which can be complicated, but yeah.
Right. So first, I think you run a risk of improper negation. And improper negation can give you, right, you'll end up with incorrect properties, and then you end up with, total mess.
Well, because technically speaking, about mathematical statements, the fact is they have to be true or false. Otherwise, they're not mathematical statements.
Yeah, don't give me that shit about fuzzy logic. That's just a function. Mm-hmm. So, we can discuss that on another podcast.
That's actually well defined. But so whenever you say assume it's false, then you are saying assume the negation of that statement is true.
Correct. But, okay, I guess to me, whenever I have tried to do a proof by contradiction, and I rarely, in fact, nowhere does it show up in my dissertation. I don't think I've ever used it in a paper.
You are far more principled than I am.
Because when I have to do it, and there are some times, I'm trying to think of a theorem off the top of my head where it's proved by contradiction, and I can't imagine another way to do it. But to me, whenever I've done that, and I've tried it. And by the way, whenever I did this, on exams in grad school, I was desperate. Oh my God, we were running out of time and I couldn't get anything. And
proof by contradiction, last resort.
Try proof by contradiction. But I think I always tried to search for what was the contradiction going to be, and then you put it together. Okay, well, if I get this, then what possibly weird is going to come out of that? Mm-hmm. I don't know if it's because I don't think about it correctly, or I just have a fairly sequential mindset when I'm proving something. But I always felt like with proof by contradiction, I'm going to have to essentially do a direct proof on the negation, so I might as well try to do a direct proof on the statement. Now, like I said, there are certain theorems, especially in analysis, where the classic proof is a proof by contradiction, and looking at it, because it's kind of a fun game, well, how many other ways are there to prove this same statement? And you can actually publish papers, right? If you have a new proof to, say, Rolle's theorem, for example, that's a paper, right? Certainly. It's a new way to prove it. That's absolutely publishable work. But sometimes you read those and you're just they proved it by contradiction, but I can't honestly see how you would have done this directly.
Mm-hmm. What's that classic question? There are infinitely many prime numbers.
That one's probably contradiction, isn't it?
That's the only way I know.
Yeah, that's the one. That must have been the one I was thinking of. Yeah, so that's a classic example. But you look at that and you're just it starts with if you're trying to prove the statement, there are infinitely many prime numbers. How are you going to do that directly? Right? You can try to look at maybe this set of prime numbers and show somehow that its cardinality is infinite directly. But what's the way we end up doing it? It's show that there are not infinitely many prime numbers. Mm-hmm. So if there are not infinitely many prime numbers, then what does that mean? Well, there has to be a largest one, right?
Yes.
So where does the contradiction come in that proof?
The way I've always seen it done is you can form a new prime which is necessarily bigger than your largest one.
Right. So what that means is if the prime set of prime numbers is finite, then that means there must be a largest one. If there's a largest one,
then you shouldn't be able to find a bigger one.
Because if I find a bigger one,
if you say there are not infinitely many primes, then there is a largest one.
Right. So if there's a finite, right, if I have a finite set of stuff, of numbers, that means there has to be a biggest one.
Yes, whenever...
Well, closed. We won't... Okay, my bad. Let's do a set of natural numbers.
You have to understand that...
All right, I was not careful. I'm sorry.
No. I'm telling anybody that's listening, you have to understand that whenever anybody says anything, mathematicians cover all the bases whenever they listen to it, so they have to look for any holes in it.
Actually, which is good, right? So if there are not infinitely many prime numbers, your alternative is that there are finitely many prime numbers, namely that the negation of the statement there are infinitely many prime numbers is there are finitely many prime numbers.
Right.
If there are finitely many prime numbers, we must have a largest one.
That's true.
So what happens? Well, we find that whatever that largest one is, I don't know, call it X, P, whatever, that thing, if I can create one bigger than that, it's not the largest one anymore now, is it?
It's true.
But the problem is because we just set, it's just a generic largest prime, if I can always create a bigger one than the new largest prime, I'm never going to stop being able to do that, which is a contradiction to the notion that the cardinality of that set is finite. Therefore, we must conclude that there are infinitely many prime numbers. How would you even do that directly?
I honestly don't know.
Right? To me, when you're dealing with cardinality, especially proving something's whether it's finite or not, I go for proof by contradiction in that one because if you're going to prove something is infinite, it seems like all of those end up being proof by contradiction, assume something is finite.
Unless you can, like you said, find a bijection with a natural numbers or something like that.
You'd have to make a counting function or some kind.
But since there is no closed form for all the primes,
Nope. Good luck.
Not that we didn't know of. If you figure one out, tell us.
Dude, I think you win a prize if you can get that one. I don't think anybody knows that one.
I think you would get a Fields Medal for that.
Yeah, probably at minimum.
Big bunch of money. So, like I said, if you figure one out, let us know.
But anyway, so that leads me to the question I thought about this morning when we were talking and what spawned this. There are certain statements in mathematics that we look at and obviously, just because I say I can't imagine another way to prove this doesn't mean that's the only way to prove this. But let's go meta for a second. Is it possible to abstract the notion of statements and proofs altogether and find the structure of a construction of a statement such that you can show that there is only one way to prove that structure of a statement?
Right. Is there a class of statements that have unique methods of proof?
Correct. As in if you prove a statement in this class, if it indeed exists, then you are the only one who proved it. As in your proof is unique and provably so. Right? We can prove that your proof is the only way to do this. Now, there are people that do work in this space. We like to get really heavy. And there are fields of study that look into computer proofs, right? Computers are proving statements. And some of those are used in something called verified protocols. So how do you prove that a computer program, for example, works all the time? Because obviously when we code stuff, then bugs happen, whatever. So from a more interesting philosophical question for those that are still listening, do you think it's possible, right? Everyone's worried about computers replacing their jobs. AI this, AI that, blah, blah, blah. I threw up in my mouth. Is it possible, do you think, for AI to replace us? As in us as mathematicians?
No.
Why not?
Because I think you need lateral thinking that computers can't make, at least not yet.
Thank you, Balios. I appreciate that.
I'll say what I said again because it was covered up by him shaking. No, I think that you need lateral thinking, which is something we're capable of.
Right. Lateral thinking being you're not just proceeding down a path, you have to reach to the side. So that's how sometimes new fields get created. For instance, algebraic statistics, right? That's statisticians and algebraists essentially reaching across mathematical disciplines to create an entirely new field. There aren't obvious connections, or at least there weren't. Of course, once something's proven, then it's like, holy cow, that's really freaking obvious, right? Those are the best proofs, right? Those are the best statements. But anyway, you didn't know those things would have a connection beforehand. You're not going to. Or even invoking a theorem, right? Mm-hmm. If I'm moving to prove that the sum of two odd numbers is even, right? That's almost algorithmic, right? You're just, it's algebraic manipulation. And computers are good at that.
Yes.
And you can actually, I'm pretty sure there are, I don't remember what the language is called. But you can program a computer to prove that. Right? It's a simple, essentially, sequence of statements. But when I have to invoke, say, Chebyshev's inequality, for example, in probability, and it means that when I invoke that, another theorem inside of one of my proofs, it means I have seen the hypotheses of that theorem, but in a different format, right? It's not just, oh, I just happened to write the exact hypotheses of this theorem while I was proving it. No, you see it, but in a different form, which means now I reach to the side and pull it in, because essentially I'd be proving that theorem all over again, but it just looked a little bit different. That's why I get to reach to the side and pull that theorem and said, well, we've already set up these hypotheses, meaning I don't have to do this original work because it's already been done. But that reaching out to the side, I don't think you can program a computer to recognize, for instance, let me try to come up with a good example. Recognizing dependency graphs and their adjacency matrix. Like when we started looking at the dependency stuff, we had to draw it out for ourselves, right? When we originally started doing this, those graphs didn't exist. We used that to try to visualize it because it was the most natural thing we could do. And once we started visualizing that way, we saw that they became directed graphs. No computer's going to see that.
No, I mean, you would almost have to have a system in place which at any given moment, like you give it a set of objects. These things are what it has to work with to prove the statement. So here's a statement, and here are its like pieces. This is what you have to work with. At every stage of that, it would have to be aware of every possible theorem and all of those objects that could apply.
It's not even just a matter of having a dictionary. It's actual intelligence,
yes.
Meaning you have
need some forethought.
You have to see it in a different form, from a different angle. It's like, I mean, I know what a horse looks like no matter what angle I see it from. Front, back, sides, whatever. I know it's a horse. Obviously, we're trying to get AI to do that kind of thing.
Right.
That's just image recognition, but we're talking about abstract image recognition. Because that's what it is, right? Mathematics is an abstract image. We can't draw a picture of it necessarily, but that's what it is.
Like for a proof, you might have to recognize that this function, which looks strange this way, is actually the integral of some other function.
It happens in statistics all the time. You'll recognize a really ugly integral, or you'll look at it, and if you multiply by a certain constant, factored something out, it's actually a probability distribution and it integrates to 1, yay. But unless you can see that, and see that, it's just this little adjustment that doesn't actually change anything, it just changes the form, it becomes a probability distribution essentially times a constant.
Those intuitive leaps I don't believe are possible with computers.
I don't think so either. That's not how they work.
I believe they're efficient, but they're not that smart.
Correct. Absolutely, it can add faster than I ever could.
Mm-hmm.
No, I think creativity cannot be replaced, and mathematicians are ultimately creative people.
Yes, it's a creative process. You are making something whenever you bring this mathematical truth to light. I believe that.
It comes with the same satisfaction that an artist or a musician gets from making something new.
Otherwise, why would you... Otherwise, there wouldn't be any handwriting in your proofs or something. There's absolutely an artistic element to it. There's a way you want to express that truth, and you want it to be bulletproof, and you want it to be the way that you chose to do it. That's artistic to me.
Now I kind of want to, do I recognize signatures in my own proofs or some kind of style? As in, like, one day when I write a textbook or something and write proofs, will people be able to recognize that those are my proofs?
Oh, this looks like the trailer proof.
Oh, yeah. That's feed the ego. There you go. Feed the ego.
I mean, like, and that's I think when we were talking about the prime numbers earlier, what I've seen, the proof I've always seen is, assume you have finitely many, which will lead to a contradiction. There has to be a biggest one, but you can make one bigger by taking all of the finitely many primes, multiplying them together, and adding one. Anyway, that's a famous proof. I believe it's known as Euclid's proof. Like, that was his. So
yes.
It can be associated with your name.
And I'm pretty sure that there are probably people that have tried to do that directly.
Yeah, that sounds hard. That sounds really hard.
Yeah, well, plus I'm not really a number theorist.
Nor am I. You know what? I this is kind of artistic bent when it comes to writing proofs. How do you like to end proofs? Do you like a proof symbol?
Okay, it depends for me. Usually I use the box, right? If I'm writing it by hand, I'll use the 2 lines.
Oh, like 2 slashes?
Yeah, 2 slashes.
Forward slashes or back slashes? Forward slashes, right?
Yes.
The top is to the right?
Yes.
Forward slash.
Why is it I can never remember which one's forward and which one's back? I think it's because, like, if I talk, which one is the thing that is back, the top or the bottom? I don't know.
Yeah, it's a bit ambiguous. Backslash is LaTeX, that's what I always think.
Okay, yeah, I like that. Now I'll remember. So if I'm handwriting it, it's slashes, 2 slashes. If I'm typesetting it, it'll be the box, most likely, unless it's a really big one. Now, I don't use QED.
See, I used to, and then whenever I got older as a student, I was like, I need to stop doing this.
Dude, QED is I will stake my life on this. I am so confident of this that if I'm wrong, go for it.
It seems so bold to put QED.
So how do you feel of me tattooing QED on my wrist then?
I think that you would stake your life on the thing that you did to earn that tattoo.
Yes, I did. I would stake my life on that dissertation.
Let's see. What other things about proofs can be made artistic? If anybody that goes to this site.
Ooh, wait, we can talk about, like, use of symbols and different math alphabets.
Yep.
Oh, I almost ran out. I was running out of symbols on my dissertation. Because I had so many sets of random variables.
You had all the alphabets going, all their italic and non-italic
I did
versions.
MathCal, MathFrac.
Certainly Blackboard.
Yeah, I used the Blackboard one.
And MathCal, like the...
Did I not say that?
I think you said math.
Oh, I used MathScript too. I did calligraphic and script. Right. No, I think I touched all of them.
Yeah, you maxed out all the.
Well, that's the kind of the thing is, like, when I don't want to if we're using, say, t as the random time of arrival, and then I need to do something with a permuted version of that or something. I don't want to just go like, okay, well, I'll call it R or something like that, right? You need to kind of stick with it. It's another way to make sure the proof is clear and flows that, okay, well, it's the slightly different T because we just kind of permuted the order or whatever.
Yeah. So it should have some semblance of T to it.
Sure. Again, that's how you follow.
Yeah. Like, do you reserve M and N for positive integers?
Yes. Yes, I do.
But, like, say, RS and T.
Ooh, can I talk about a small pet peeve? I don't like the Greek letter the lowercase Greek letter pi for stationary distributions.
Oh, I see that a lot, too.
Oh, I don't like it. It bothers me. Pi is a constant. Stop.
You find something
And capital pi is product. Like, they're reserved. And I don't, like, what would you use? I don't know, because rho's a correlation coefficient typically. And P, little p, what are you going to do with that? Big P is probability.
Well, this is this is not a sales pitch, but there are commercial sets of fonts which make available entire alphabets like that for you. So, like, there is a little script P that you could use that is sufficiently different from the...
Yeah, that's true.
Of course, you're going to have to pay for that.
You can design some. We'll offer that as a service on the Math Citadel.
Yeah, now that is something I won't do for free.
For a bunch. Yo, you shouldn't. Honestly, you shouldn't. Art deserves to be paid for. Good art deserves to be paid for. Good research deserves to be paid for. Good thought deserves to be paid for. You know, just because we would do it no matter what doesn't mean it's not worth.
That's a lot of work too. I mean,
it takes me days to write a post.
Yes, it does.
It takes me weeks to get a paper up. It takes me months to do new research.
Yeah, like if you can imagine.
And this isn't like months of like, oh, it's like 30 hours a week or something. No. No, it's a real work day every day. Like if you can imagine, like a moment ago, you made a statement. You said like there has to be a largest member of the set. And both of us were like, well, hold on. Imagine examining every single statement you make in a piece of paper just like that. Every single statement is analyzed for where it could fall. Well, yeah, you have to be willing to try to break every step of your process, right? It's not proven until you are sure that you cannot break it anywhere.
It takes time to be that sure.
It does, because in fact, there was an error that I made in a draft of the paper on the generalized multinomial distribution. I incorrectly concluded that if you permuted the weights, paper coming soon, I realized I haven't actually published that as a paper. My bad. I'll get that up. But if you permuted those weights, no big deal, everything's totally fine. Well, what happened when I went back to actually write out the paper and include that section was I always go back and I reprove everything, right? I go through the proof not by just looking at it as if I were editing it, but literally throwing the proof aside, taking the statement, and starting over. And making sure that I can reprove it, and either, 1, it'll become more elegant, 2, I'll find it's right, or 3, as it was in this case, I find that I made a serious error. And it's so bad the statement actually wasn't true. But what happened, it actually led to, oh, yikes, well, it's not true. Well, under what conditions is it? Hey, look, new paper,
right.
Working on it.
As a matter of fact, if you are this sort of person that takes a look at theorems, and you are on occasion seeing those in a textbook or written somewhere else, notice the carefully constructed hypotheses for every one of those theorems. There's a reason it's there. There's a reason those hypotheses are there. And
the elegance in those proofs, too, and it looks very intimidating when you're first starting out as a mathematician, just like, how do you get a proof that nice? It doesn't come overnight, right?
No.
Just because it takes you maybe even an entire class period to study it and understand the proof, sometimes it took that professor or mathematician or person years to make sense. Like the Weierstrass theorem, I think, took years.
I recall studying the proof of the Lebesgue differentiation theorem under Dr. Korzeniowski took several class periods.
And it took him years to complete that proof.
I mean, it was 5 pages in a textbook, and it took Dr. Korzeniowski said, so it'll be about 30 blackboards.
Yeah, that one was intense.
It was very, and you needed to pay close attention, several lemmas.
Yeah, I almost, when it's that big, I almost have to go just work it out for myself.
I needed to self-study with that one, too, because it's a big deal.
Yeah, that's a big one. But these things, the most elegant, simple conclusions are the ones that sometimes take years. And just as I feel like you can't measure a good computer application or program by the number of lines of code written, which annoyingly enough is actually kind of how they do it in industry. Well, how many lines of code have you written? I'm an experienced programmer. I've written over 3,000 lines of code.
Yes, I've been counting.
Well, is that really what we need to measure by? Is it like, imagine me saying I'm such a good mathematician. I've written 3,000 lines of proof.
Yeah.
And be like,
wow, you could have saved yourself some space in a lot of these. Or
sometimes there are even mathematicians that are known for one major theorem. Not even just life-changing theorem. I mean, generational, entire field-changing and expanding theorems. And when you look at the proof, it's maybe half a page.
Right.
Right? You cannot measure things by stupid metrics like that, especially in mathematics. So it's not like this massive, complicated piece of machinery. The best stuff is the stuff that is simple from first principles and elegant and informative. That's how you take mathematics and you build other fields off of it.
I find that that's also the stuff that sticks with you the most.
Yes. I mean, like the prime numbers proof. Elegant. Very elegant.
And I remember it.
And you remember it.
The first time I encountered that proof was years ago now. It's in...
God, I don't even remember, yeah. We're not going to talk about how long
I'm
ago that was.
pretty sure it was the first problem in Apostol's book.
Is it really?
I think it's the first exercise.
Oh, we spent too much time with that book.
Yeah.
Actually, I think I'm like 99% sure you're right.
I'm pretty sure it is. Like, I almost feel like I can recite the text of the problem. Show that there are infinitely many primes. And then
Should
in
we
parentheses...
get out more?
Hold on, I gotta finish. And then
Okay.
in parentheses, a proof was known to Euclid.
Reach over there and give me a copy of that book.
Which one? We have several.
Well, give me the Apostol one.
I know, we have several editions. Which one do you want, international or non-international?
It's the same text, isn't it?
Yes.
Give me this dark. Just pick one, you. People listening are gonna be like, okay, all right, fine. Let's test you on this, right? First, I'm opening Apostol. By the way, we've reviewed that on our site. Obviously, we have a great fondness for this particular book.
That book is beautifully typeset, by the way, just a note.
Did you actually make a comment on that? You were supposed to.
I didn't put that in the review.
Why
yet.
not?
Well, I will. I'll add it.
What the heck? Okay.
That book may be perfectly typeset to me.
Oh, that's a strong statement.
I said to me. There's some... Now we're in the realm of the subjective.
All right. Hold on, I gotta get to the exercises. All right. Chapter 1, exercises. All right. Yes, Jason is absolutely correct that the first exercise in Apostol's analysis book is to prove that there is no largest prime. And the text... don't cheat.
I already did my recital. So, like,
Do it again.
Okay.
What is the text of that problem?
I mean, I said prove that there are infinitely many primes. I think now that you just said it's prove that there is no largest prime.
Yes.
Okay.
Yes,
Same
it is. That
thing.
is the text. But what does it say in parentheses?
A proof was known to Euclid.
Yes. Okay. So, this is not helping our image of people not thinking we're totally weird.
I am not going to apologize for appreciating that book.
Actually, like, I'm really impressed.
Yeah.
Not gonna lie. I'm actually really impressed by that. I've spent... I think I don't know if I could recite stuff about other things, but I definitely, like, the calculus book I taught out of when I was teaching at Georgia Tech, there was a point where, like, I could tell you almost what page certain topics were on, because I taught for so many semesters there.
Oh, yeah, you got a good familiarity with the book.
Yeah. We should end our ramblings.
Yeah, okay.
Yeah,
so
they're not
we're
going to listen to our ramblings that much longer.
Okay, so yeah, at this point...
That was our most, I think that was our most mathematical discussion. Mm-hmm. So, appreciate you guys listening.
It's true that if asked, we can certainly talk at length about proofs and the things that go into proofs.
There was a pre-discussion before this discussion, by the way.
Yeah, typing proofs and how to type them.
Yeah, but thank you again for tuning in to our third episode. We like to know that you guys listen in and remember that as weird as we are still sort of human.
Absolutely are, I promise.
Find us on Twitter at Math Citadel if you want to follow the official account. You can also reach me at Mathpocalypse.
And I'm Jasonographer.
And check out our Patreon account if you like the stuff that you're hearing or like the site or want to support it. Then the Patreon link is on the Math Citadel website under support. All right. See you guys later.